Hi students, welcome back to our online class. Today I am really very happy because after a long time I got the chance to teach you. Right. Today I am going to talk about one of the important topic from the chapter current electricity, that is Wheatstone bridge. The name of the topic is Wheatstone bridge. Wheatstone bridge or Wheatstone network. Before going to this, first let us recall the previous topic, that is Kirchhoff's laws. Kirchhoff's laws. Right, there are two Kirchhoff's laws. Kirchhoff's first law. Kirchhoff's first law is also called Kirchhoff's current rule. And next, Kirchhoff's second law. Kirchhoff's second law is also called Kirchhoff's loop rule. So current rule and loop rule. So there are two Kirchhoff's laws. Right. Kirchhoff's first law is based on consequence of conservation of a charge, whereas Kirchhoff's second law is based on the consequence of a conservation of energy. Right. So according to Kirchhoff's first law, the algebraic sum of the currents meeting at any junction in an electrical circuit is equal to 0. So this is Kirchhoff's current rule or Kirchhoff's first law. According to Kirchhoff's first law, algebraic sum of the current meeting at any junction is equal to 0. Right. So this is based on the consequence of a conservation of a charge. Right. Next, second law, the algebraic sum of the products of the current and resistance in each part of the any closed circuit is equal to the algebraic sum of the EMFs in the closed circuit. EMFs in the closed circuit. So second rule, the algebraic sum of the product of the current and resistance in each part of the any closed circuit is equal to the algebraic sum of the EMF in the closed circuit. EMF in that closed circuit. So this is the first rule, that is Kirchhoff's current rule, and this is the second rule, that is Kirchhoff's loop rule. So this is Kirchhoff's first law and this is Kirchhoff's second law. Right. So here the Wheatstone bridge is one of the application of Kirchhoff's law. One of the application of, or one of the important application of Kirchhoff's law is Wheatstone bridge. It's used to find the unknown resistances in the electrical circuit. Unknown resistance in the electrical circuit. And next, it is also used to compare the resistances. Compare the resistance. So Wheatstone bridge is one of the electrical circuit which is used to find the unknown resistance, and also it is used to compare the resistances. It is used to compare the resistance. So let us see one by one. Right. So first we go for the construction of a Wheatstone bridge. Construction of Wheatstone bridge. Right. The Wheatstone bridge consists of four resistances. Four resistances. Okay. So this is a symbol of resistance. Symbol of resistance. So this is positive end and negative end. Right. So here the Wheatstone bridge is one of the electrical circuit. It consists of four resistances. They are P, Q, R and S. The name of the four resistances P, Q, R and S. Suppose the four resistances are connected like this. Right, the four resistances are P, Q, R and S. Wheatstone bridge consists of four resistances P, Q, R and S. They are connected in the form of a closed loop. They are connected in the form of closed loop, that is A, B, C, D. Right? The four resistances P, Q, R and S connected to form a closed loop, that is A, B, C, D, A. A, B, C, D, A. Right. Right. So here across the points B and D there is a sensitive galvanometer or a sensitive galvanometer, that is G, whose resistance is G. is connected across the points B and D. Right? Across the points B and D, a sensitive galvanometer is connected like this. Right? Across the points A and C, an electric cell of EMF is connected. This is positive terminal of the cell and this is a negative terminal of the cell. So across the points A and C, an electric cell of EMF is connected, and across the point B and D, a sensitive galvanometer is connected. We know that galvanometer is a sensitive device which is used to detect whether the electric current flows through the circuit or not. Right? So across the point B and D, a galvanometer is connected. Across the point A and C, an electric cell of EMF E is connected. Right? Okay. So what is electric cell? Electric cell is a source of electric current. Source of electric current. Suppose the cell delivers an electric current I. Right. So let I be the current from the cell. Right. When the current I enter the point A or enter the junction A, it is divided as I1 and I2. Right? So I be the net current or total current delivered by the cell. When this current enter the junction A, it is divided as I1 and I2. I1 and I2. Right? Here the current I1 is flowing through the resistance P, whereas the current I2 is flowing through the resistance R. Right? At point B, the current I1 is divided as IG and I3. The total current from the cell I is divided as I1 and I2 at the junction A. And the current I1 is flowing through the resistance P and enter the point B. At the point B, the current I1 is divided as IG and I3. Here IG, the current flowing through the galvanometer. Current flowing through the galvanometer. So the IG current is flowing through the galvanometer of resistance capital G, and the current I3 is flowing through the resistance Q. Flows through the resistance Q. Right. At point D, the current I2 and the current IG is combined together, that form I4. Right. So the IG current is flowing through the galvanometer and I2 current is flowing through the resistance R. They are meet at point D and they are combined together, that form I4. Right. And I4 is flowing through the resistance S and I3 is flowing through the resistance Q. And these two currents are meet at point C. Then we can get the total current I. Right? So I be the current from the cell. This current is flowing through this path and enter the point A, and it is divided as I1 and I2. The I1 is flowing through the resistance P and I2 resistance flowing through the resistance R. The current I1 enter at point B and it is divided as IG and I3. IG flowing through the galvanometer and I3 is flowing through the resistance Q. Right. Here IG current and I2 current is meet at point D and they are combined together, that form the current I4. The current I4 is flowing through the resistance S. Right. And the current I4 and I3 once again combined, that form the total current, that is I. So this is construction of a Wheatstone bridge or Wheatstone network. Wheatstone network. Already I told, Wheatstone bridge is one of the electrical circuit which is used to compare the resistances, and also it is used to find the unknown resistance in the electrical circuit. Unknown resistance in the electrical circuit. Right. The working principle of Wheatstone bridge is null deflection. Null deflection. The working principle of Wheatstone network is null deflection. Right. So that is the ratio of adjacent resistances are equal. The ratio of adjacent resistances are equal. Then no current flowing through the galvanometer. No current flowing through the galvanometer. So this is working principle of meter bridge. Right. Suppose these two are adjacent resistance. The ratio of these two resistances equal to remaining two resistance ratio means then the amount of current flowing through the galvanometer is 0. So this is called null deflection. The working principle of Wheatstone bridge is null deflection. Null deflection means the ratio of adjacent resistance, two adjacent resistance are equal, then no current flowing through the galvanometer. So this is null deflection, and which is the working principle of Wheatstone bridge or Wheatstone network. Right. Next, okay. We know that there are two Kirchhoff's laws, Kirchhoff first law and Kirchhoff second law. Kirchhoff first law is also called Kirchhoff's current rule, and Kirchhoff second law is also called loop rule or Kirchhoff loop rule. Right. Now, just you apply Kirchhoff first law or Kirchhoff current rule at the junction B and at the junction D. Okay, at junction B and at junction D, we want to apply Kirchhoff first law or Kirchhoff current rule. Right. What is the Kirchhoff current rule? The algebraic sum of the currents meeting at any junction is equal to 0. The algebraic sum of the currents meeting at any junction is equal to 0. So this is Kirchhoff's current rule. And a sign convention is there. That is, the current flowing towards the junction should be taken as positive, whereas the current leaving the junction should be taken as negative. Right? Suppose at junction B, there are three currents. One is I1, another one is IG, and third one is I3. Right? Here, by sign convention, the current I1 is flowing towards the junction, so it should be taken as a positive. Right? Whereas the current IG and I3 leaving the junction, so they should be taken as negative. Right? First, applying Kirchhoff's current rule at junction B, at junction or at point B, right? So according to Kirchhoff's current rule, the algebraic sum of the currents meeting at any junction is equal to 0. The algebraic sum of the currents meeting at any junction is equal to 0, right? A sign convention is there, that is, the current flowing towards the junction is positive and the current leaving the junction is negative. Right? At junction B, the current I1 is flowing towards the point B, so it is taken as a positive. Right? That is I1. Right? And the current IG is leaving the junction B, so it should be taken as a negative. And I3 also leaving the junction, so it is also negative, which is equal to 0. Right? Algebraic sum of the currents meeting at any junction is equal to 0. This is Kirchhoff's current rule. Kirchhoff's current rule. Right? Or I1 minus IG minus I3, which is equal to 0. Right? So this is taken as equation number 1. Equation number 1. Right? So Kirchhoff current rule is applied at the junction B. After applying Kirchhoff current rule at junction B, we get a first equation, that is I1 minus IG minus I3 equal to 0. Right? Once again applying Kirchhoff's current rule at junction D. At junction D. Right? First at junction B. Okay, the Kirchhoff current rule is applied. We get first equation I1 minus IG minus I3 equal to 0. Right? Then applying Kirchhoff current rule at the junction D. Right? At junction D, the current I2 is flowing towards the point D and IG flowing towards the point D, but the current I4 leaving the point D. So by applying Kirchhoff current rule, I2 positive, IG also positive, but the I4 is a negative, minus I4, right, which is equal to 0, right, or I2 plus IG minus I4 equal to 0. So this is equation number 2, right. So first applying Kirchhoff current rule at junction B, we get I1 minus Ig minus I3 equal to 0, first equation. And after applying Kirchhoff current rule at junction D, we can get another equation, that is to I2 plus Ig minus I4 equal to 0, right? Next, we want to apply another Kirchhoff law, that is second law or loop rule, right? What is the Kirchhoff loop rule or Kirchhoff second law? According to Kirchhoff second law, in the closed circuit, the algebraic sum of the products of the current and resistance in each part of the any closed circuit is equal to the algebraic sum of the EMFs in the closed circuit. The algebraic sum of the EMF in that closed circuit, right? That is summation IR is equal to summation E. Right, algebraic sum of the products of the current and resistance in each part of the any closed circuit is equal to the algebraic sum of the EMF in that closed circuit, right? So in this Wheatstone network, it is necessary to apply Kirchhoff's second law, for two closed loops. So first, let I take first closed loop A, B, D, A to B, then B to D, and D to A, right? In this closed loop, we want to apply Kirchhoff's second rule, that is the Kirchhoff loop rule, right? Applying Kirchhoff's loop rule for the closed loop A, B, D, A, right? For the closed loop, for the closed loop A, B, D, A, right? Applying Kirchhoff loop rule for the closed loop A, B, D, A, right? So Kirchhoff loop rule, summation of I into R is equal to summation E, right? In this closed loop, there is no electric cell. That is there is no EMF. So the summation E value is 0. Right? Summation E value is 0 because in this closed loop A, B, D, A, there is no electric cell. So summation of net EMF value is 0. So it should be taken as 0. Right? And next, in the closed loop A, B, D, A to B, a current I1 is flowing through the resistance P. Right? So therefore, I1 into P, right? Next, B to D, the current Ig is flowing through the galvanometer of resistance capital G. So, plus Ig into capital G. Next, D to A, the current I2 is flowing through the resistance R, right? Actually, the assumed direction is from D to A. But actually, the current flowing in this path is from A to D. By same convention, if the assumed direction and the actual direction are in opposite direction, the current I2 should be taken as a negative. If the assumed direction and actual directions are same, the current is taken as positive. And the assumed direction and the actual direction are opposite, then the current value is taken as negative. Right here. In the closed loop A, B, D, A, the assumed direction is A to B first. The actual current direction also the same. So I1 is taken as a positive. And next B to D, the assumed direction and the actual direction of a current are same. So Ig value is taken as positive. So that is why plus Ig into capital G. But from D to A is assumed direction, but actual direction is A to D because the current I2 is flowing from A to D. But we assume the current direction is from D to A. So opposite direction. So that is why the I2 value is taken as negative. So plus of minus I2 into R is equal to 0. Right? Or I1P plus Ig into capital G minus I2 into R, which is equal to 0. So this is taken as equation number 3. So by applying Kirchhoff's loop rule for the closed loop A, B, D, A, we can get, third equation, that is I1 into P plus Ig into capital G minus I2 into R is equal to 0, right? Once again, applying Kirchhoff's loop rule for the entire closed loop, that is A, B, C, D, A, right? Now applying Kirchhoff's current rule, for the loop A, B, C, D, A. The loop A, B, C, D, A. Right. In this closed loop also no electric cell. So net EMF in this closed loop is 0. That is algebraic sum of the net EMF value is 0. Right. And next to left hand side, the algebraic sum of the products of current and resistance. Right. First A to B. A to B, I1 current is flowing through P. So product I1 into P. I1 into P. Here the assumed direction A to B and actual direction of a current I1 also A to B. So it should be taken as a positive. So that is why I1 into P. Right. Next B to C. From the path, in the path B to C, the assumed direction B to C and actual direction of current I3 also B to C. So I3 is taken as positive. So product I3 into Q, right, plus I3 into Q. Right. Next A to B, next B to C, then C to D. Right. Here the C to D path, the assumed direction is from C to D, but the actual direction of a current I4 is from D to C. So assumed direction and actual directions are opposite direction. So it should be taken as negative. So plus of minus I4 into S. Plus of minus I4 into S. Next D to A. D to A, assumed direction, actual direction is A to D because the current I2 is flowing from A to D. So I2 should be taken as a negative. So that is why plus of minus I2 into R, right, which is equal to 0. Why? Because there is no electric cell in this closed loop, that is the summation of E value is 0, right? Or I1P plus I3Q minus I4S minus I2R, which is equal to 0. So it is taken as equation number 4. Equation number 4, right? Okay, suppose in this electrical circuit, the point B and D have same electric potential, or on other hand, the potential difference across the point B and D is 0. Potential difference across the point B and D or potential difference across the galvanometer is 0 means the amount of current flowing through the galvanometer is 0. Right? So once again I repeat, the point B and D have same electric potential. Okay, suppose electric potential at point B is V and electric potential at point D also V. What is the potential difference? Potential difference between the point B and D, V minus V, 0. So potential difference across the point B and D is 0 means there is no electric current flowing through the galvanometer. There is no electric current flowing through the galvanometer. So first we assumed the electric potential at point B and D is same. Electric potential at point B and D is same means the potential difference between the point B and D is 0. In this situation, the Ig value is 0 because no current flowing through this path. Right? So if the potential at the points B and D are same. If the potential at the points B and D are same, then no current flowing through the galvanometer. That is, Ig equal to 0. So this is very important condition while we are dealing with the Wheatstone bridge. If the electric potential at point B and D are same or equal, no current flowing through the galvanometer, so Ig value is 0. Ig value is 0, right? Suppose if this condition is satisfied, then substitute Ig equal to 0 in equation number 1 and equation number 2 and equation number 3, because in this 3 equation Ig is there. Okay, if this condition is satisfied, then we want to apply Ig equal to 0 in this 3 equation, right? So substitute Ig equal to 0 in equation number 1, equation number 2 and equation number 3. Right? Substitute Ig equal to 0 in equation number 1, 2 and 3. Right. In the Wheatstone network, the potential at point B and D are the same, no current flowing through the galvanometer. That is, Ig value is 0. Now substitute Ig equal to 0 in equation number 1, equation number 2 and equation number 3. Right. So by applying Kirchhoff first law and Kirchhoff second law in this electrical network, we can get 4 equations. This is equation number 1, this is equation number 2, equation number 3 and equation number 4. In equation number 1, 2 and 3, Ig is there. So if the point B and D are same, Ig value is 0. If this condition is applied or this condition is satisfied, then Ig equal to 0, substitute Ig equal to 0 in the equation number 1, 2 and 3. Right. Now, substitute Ig equal to 0 in equation number 1, then equation number 1 becomes I1, Ig value is 0, so leave it. Next to minus I3, which is equal to 0, or I1 equal to I3. So this is equation number 5. Right. Next, the equation number 2 becomes I2, Ig value is 0, so leave it. Next to minus I4 equal to 0, or I2 equal to I4. So let it be equation number 6. Next, equation number 3 becomes I1P, I1P, Ig value is 0. Next, minus I2 into R equal to 0, or I1P is equal to I2R. So this is equation number 7. Right. Now divide equation number 7 and equation number 4. Right. Here the equation substitute I1 is equal to I3 and I2 is equal to I4 in the equation number 4. Right. Okay, listen. Substitute here I1 equal to I3, I2 equal to I4. Substitute I3 equal to I1, I4 equal to I2 in equation number 4. Substitute equation number 5 and equation number 6 in equation number 4. Right. Then the equation number 4 becomes, right, I1P and I3 is equal to I1. So therefore instead of I3 we can write I1. So I1 into Q. Next, I4 equal to I2. So instead of I4 here I2 minus I2 into S. Right, then minus I2R. I2R. Right, which is equal to 0. Here I1 are common, so take outside. I1 of P plus Q. Right, here minus I2 common, so take outside. Right, minus I2 of S plus R, or R plus S. Right, which is equal to 0. Or I1 of P plus Q is equal to, if minus I2 of R plus S is taken to this side and it becomes a positive. So I2 of R plus S. So this is taken as equation number 8, right? Now divide equation number 8 and equation number 7. Right. So equation number 8, left hand side, I1 of P plus Q. In the equation number 7, left hand side, I1P. So divided by I1P equal to, in equation number 8, right hand side, I2 of R plus S. In the 7th equation, right hand side, I2R. I2R, right? I1 cancel, I2 cancel. So P plus Q divided by P is equal to R plus S divided by R. R P divided by P plus Q divided by P is equal to R divided by R plus S divided by R. P cancel, R cancel. So 1 plus Q divided by P is equal to 1 plus S divided by R. So plus 1 both side cancel. So Q divided by P is equal to S divided by R. Or taking reciprocal on both sides, P divided by Q is equal to R divided by S. So this is called bridge balanced condition. Here the equation P divided by Q is equal to R divided by S is called bridge balanced condition. Bridge balanced condition, right? Here the Wheatstone network is in balanced condition, no current flowing through the galvanometer. When the current flowing through the galvanometer is 0, if the point B and D having same electric potential. The point B and D having same electric potential, then potential difference across the galvanometer is 0. If there is no potential difference across any 2 points, no electric current flowing through the circuit. So Ig value is 0. Okay, put Ig equal to 0 in equation number 1, 2 and 3. We can get I1 equal to I3, I2 equal to I4, I1 into P is equal to I2 into R. Substitute I3 equal to I1, I4 equal to I2 in equation number 4. The equation number 4 becomes I1 of P plus Q minus or equal to I2 of R plus S. Right, now divide equation number 8 and 7. Okay, after simplification we can get P divided by Q is equal to R divided by S. So this is called bridge balance condition. Bridge balance condition. Right, bridge balance condition in Wheatstone network is P divided by Q is equal to R divided by S. Already I told what is the working principle of a Wheatstone bridge, that is null deflection. Okay, what is null deflection means? The ratio of two resistances, in both the arms are equal, then no current flowing through the galvanometer. So this is called null deflection, which is the working principle of a Wheatstone bridge. Right. Already I told what are the uses of a Wheatstone network. Okay, first the Wheatstone network is used to compare the electrical resistances. Next, it is used to determine the unknown resistance. Suppose if we know the values of two adjacent resistances, or the value of two adjacent resistances, we can compare another two resistance ratio. Okay, we can compare another two resistances ratio, right? And next, if you know the value of any three resistances, suppose P, Q, R values are known, then by using the bridge balance condition, we can determine what is the value of S. Suppose P, R and S values are known, then Q value can be calculated. Or P, Q and R values are known, then S value can be calculated. So Wheatstone network is used to determine the unknown resistance, and also it is used to compare the resistances. If we know the values of two adjacent resistances, we can compare the ratio of another two resistances. So Wheatstone bridge is one of the electrical network which is used to compare the resistances, ratio of two resistances, and also it is used to find the unknown resistance. The working principle of Wheatstone bridge is null deflection. In the null deflection method, there is an equation, that is P divided by Q is equal to R divided by S. This is called bridge balance condition. Bridge balance condition. Right, so based on a bridge balance condition, some problems are there in our textbook. Okay, let us see that. Right, based on a bridge balance condition, one of the problem is given, that is example 2.23 in our textbook. Right, the problem is, in a Wheatstone's bridge, the resistance P value is 100 ohm and Q value is 1000 ohm and R value is 40 ohm. If the galvanometer shows zero deflection. In Wheatstone bridge, galvanometer shows zero deflection means the Wheatstone bridge is in balanced condition. Balanced condition, right? Okay, from the balanced condition, okay, we want to determine the value of S. Value of S, right? First, the given values in this question are P is equal to 100 ohm, Q is equal to 1000 ohm, R equal to 40 ohm. What we want to find out? The unknown resistance value, that is S. So S value we want to find out. Right. So here the galvanometer shows zero deflection. So the Wheatstone bridge is in balanced condition. Right. Okay, solution. According to Wheatstone bridge balance condition, P divided by Q is equal to R divided by S. P divided by Q is equal to R divided by S. Right. Or we need S value. Therefore, S is equal to Q divided by P into R. Okay. S is equal to Q goes to numerator and P comes to denominator. If P and Q is taken to the side, so we need S. Therefore, S is equal to Q divided by P into R. Right. Now substitute the known values in this equation. Then S is equal to Q value is 1000 and P value is 100 into R value is 40. R value 40. Right. 0, 0 cancel. Right. Therefore S equal to 10 into 40. 400. So the key sentence in this question is galvanometer shows zero deflection. If the galvanometer shows zero deflection, the Wheatstone bridge is in balanced condition. The bridge balance condition is P divided by Q is equal to R divided by S. By using this condition, we can find out the value of the value of unknown resistance, and that is S. Right? S is equal to Q divided by P into R. P value, Q value and R values are given. Substitute here, then we can get S is equal to S value, that is 400 ohm. 400 ohm. Right. Next problem. Example problem 2.24. Right. What is the value of X? What is the value of X when the Wheatstone network is balanced? What is the value of X when the Wheatstone network is balanced? Wheatstone network is given, right? There is a resistance X. So we need to calculate the X value. Okay. Here the P value, Q value and S values are given. P value is 500 ohm and Q value is 800 ohm. S value is 1000 ohm. Right. In the place of R, in the Wheatstone network, in the place of R, there are two resistances. One is X, unknown resistance, and another one is 400 ohm resistance. Here X and 400 ohm resistance are in series, right? If two resistances are in series, suppose the resistance R1 and the resistance R2 are connected in series, then the total resistance of the combination is RS is equal to R1 plus R2, right? So this is very familiar to you. So here X and 400 ohm are in series. So sum of these two value is equal to R. So that is why R is equal to X plus 400. R value is equal to X plus 400, right? Here the Wheatstone network is in a balanced condition. Okay, in the question the Wheatstone network is balanced. So the bridge balance condition is there, that is P divided by Q is equal to R divided by S, right? By using this bridge balance condition, we can find out what is the value of X in this electrical network, right? Okay. So first, we want to write what are the given values in the given question. First, P is equal to 500 ohm, Q is equal to 800 ohm. In the place of R, there are two resistance X and 400. These two are in series, so that is why R is equal to X plus 400. R is equal to X plus 400. Next, S value is 1000 ohm. Right. What we want to find out? X value. Right. Here, the Wheatstone network is in balanced condition. Therefore, according to bridge balance condition, P divided by Q is equal to R divided by S. P divided by Q is equal to R divided by S. Right. P value 500, Q value 800 equal to R value X plus 400, S value 1000. Right. Simplification. In both the denominators, both side denominators, 0 is there. So first cancel that. Right. Next to 500 divided by 8 equal to X plus 400 divided by 10. Right. Or X plus 400 equal to, keeping X plus 400 here, and 10 is taken to that side. Then we can get 500 into 10. Okay, 10 goes to numerator. So 500 into 10 divided by 8. Right, which is equal to, right, simplification, 4 2s are 8, 5 2s are 10. Next, 2 2s are 4, 250 times of 2, 500. 250 cancel, 125. 125 into 5, 625. So X plus 400 is equal to 625. Therefore, X is equal to 625 minus 400. X is equal to 625 divided by 400. 625 minus 400. 5 2 2. So 225. If X value is 225 ohm, okay, then only the Wheatstone network is in balanced condition, right? In the given question, Wheatstone network is balanced condition is given. So from that condition, X value wants to find out. By using the relation P divided by Q is equal to R divided by S, we can calculate the value of X. The value of X is 225 ohm. 225 ohm. So these two problems are very simple problems, right? So Wheatstone network is one of the electrical network which is used to determine unknown resistances, and also it is used to compare the resistances. It is one of the important application of Kirchhoff's law. The working principle of a Wheatstone network is null deflection. If no current flowing through the galvanometer means the Wheatstone network is said to be in balanced condition. The bridge balance condition in the Wheatstone network is P divided by Q is equal to R divided by S. Right. Thank you, students.